Hello, I would like to explore how you would find the rotational inertia of a rod about its end when it has a variable density that gets more and more dense at some rate b as it gets further and further to the right. So, what do we know? We know the density varies according to bx. We know the total mass is m and the total length is L. And we want to find rotational inertia about the left-hand side. So I'm just going to start with something real easy. I'm going to start with my basic equation for rotational inertia. That's our definition. Okay. Now I'm going to explore how to get rid of this dm and get it in terms of distance stuff. I'm going to use my density ideas to do that. I am told my density, lambda, is equal to bx, and lambda is also equal to mass per distance here, the linear mass density. So I can set those two equal to each other. Bx is equal to dm dx. And I can get dm by itself. That's going to be bx dx. And so now I can get rid of that dm over here and get it in terms of positional stuff. The further out I go, the more mass I'll have for a given chunk size, is what this says. So I'm going to go ahead and substitute that in here. Instead of dm, I'm going to write this stuff. Since I have it all in terms of distance, I'm going to go from the left side all the way over to the right-hand side, the full length of this guy. Next, I can do my math. And I'm going to have b as a constant, comes out in front. I'm basically just going to be integrating x cubed from 0 to L, which is pretty straightforward mathematically. And out of that I can get b L to the 4th over 4. But so what? What does that actually mean? So, how would this compare to a uniform rod? Okay, so if we had a rod that was uniform density, it's not more stuff on the right hand side than it is on the left, it's just the same all the way across. How would that compare? Well, pretty common equation, you can go look it up easily enough. A rod about its end, if it's uniform density, is 1/3 ml squared. So let's keep that in mind. Okay, so let's get it something to a point that looks like it's in terms of M and L, not this B thing. So I'm going to go down here. Yo, what is B? Can we figure that out? Okay, so remember our totals are a total mass of m and a length L. I'm going to make a little graph of the mass as we go across. Mass is a function of s of x and distance x. Now if we go L across until we get to the total mass. If we had this uniform rod and I was halfway across this thing, I only had half the length of it, I would have half the mass. And so that would look something like this. Okay, if I was half the way across, I'd have half the mass. It's like a linear relationship. But I do not have that. I have something that looks a little more like this. Let me show you why. So this is uniform, and this is non-uniform. I'll color code these maybe here. This is going to be non-uniform. Okay, so we already did our density treatment here, right here. Okay, so I'm going to go down here. I'm going to say a little chunk of mass. I could get an equation for the total mass of this thing as a function of distance by taking my density equation here and working with it. So we figure out bx dx. Well, let's get the total mass, 0 to all mass. We're going to integrate this thing from 0 to the whole length. This would just give me m on the left-hand side. Over here I get bx squared over 2. From 0 to L is just going to be bl squared over 2. Okay, so I have this. If I want to get what my b is equal to, it's going to be 2m over L squared equals b. Okay, so if I take this and I take this idea and I just do an indefinite integral from 0 to m, and this side just bx dx, I get out of here an m as a function of x is equal to something like this, which is going to look like this blue line here. The further out you go, the more rapidly you're gaining mass. Okay, so there's a little bit insight about what b is and how the mass behaves over the distance for the whole object. So now I'm going to go up here and I'm going to apply this to this thing. My I is equal to my b, but I figured out my b was this, 2m over L squared. L squared. And then I have L to the 4th over 4. And I can this, that's going to be 1/2 ml squared when we cancel out some stuff here. Okay. Now, let's compare our uniform rod to this one. So, this guy is going to have more of his mass further out from this axis of rotation than this guy. And so we would expect to get rotational inertia that's more for the same mass and length than the uniform rod with the same mass and length. And indeed, 1/2 is more than 1/3, and so we get a great outcome for that, and that answer makes sense for what we have. So indeed, our rotational inertia is greater for a non-uniform rod. Cool. So this walked you through how to take a non-uniform density and apply that to our foundational equation for how we calculate rotational inertia. And here's some additional insights for how the total mass of the rod would change as we get further out. The longer it gets, the more massive our non-uniform rod is getting. Okay. All right, thanks everybody.